Hello and welcome to this mystical chemistry walkthrough of the Carbonyls and Optical Isomerism practice test. Okay, so in question one, our first part is to do the first step of the mechanism. In order to be able to access this, of course, we have to first be able to draw the structure of the molecule that we're interested in. So we've got 2-methyl-butanal. So we should be able to recognise that, of course, butanal is the carbonyl where it's on the end carbon. So it's the C double bond O on the end carbon. And, of course, we've got 2-methyl, so we know we've got a branch coming off on carbon 2. Like so. Please note I've used CH3 and CH2 in places where that's not actually involved in the mechanism, so we don't need to show all the bonds. I didn't do that around the functional group, where seeing the bonds actually is really important. Okay, so we're told we've got sodium borohydride, which, of course, is a reducing agent. We're told that in the question. It does reduce aldehydes. Now, the simplified mechanism that we use for this is actually treating it like it is a hydride ion on its own. The reality is actually it's not a hydride ion that does the reacting, but the simplified version of the mechanism does do a good job of explaining what's happening, which is why it's acceptable to use it in these sorts of circumstances. So a hydride ion is H-. Okay, so we have to be familiar, of course, with the difference between a hydrogen ion, which is H+, and a hydride ion, which is H-. You'll only come across the hydride ion really in contexts where we've got something like the sodium borohydride, or the other example is the lithium aluminium hydride. Okay, so in a mechanism like this, yes, you can memorize it. If you just know this mechanism, you can just write out the curly arrows. But if you can't remember it, you can figure out what's going to be happening in this reaction. A hydride is a hydrogen atom that has gained an extra electron. It means that it is a really good nucleophile. Does the question tell us about the fact that it's a nucleophile? No, it doesn't. So you would be expected just to kind of figure this out. We can tell when we look at the molecule, looking at the aldehyde, that we've got a delta positive carbon. Okay, now you wouldn't be expected to write in the delta positive carbon and the delta positive delta negative oxygen, but I've just put them in just so we can see what's kind of happening here. It is logical then that the hydride is going to be able to attack the delta positive carbon. When we say attack, generally what we mean is form a bond. So we represent this, of course, with a curly arrow. Curly arrow is the movement of a pair of electrons, which means it always needs to come from the pair of electrons, which I've already drawn in on my hydride, so I've already drawn my lone pair in, and the curly arrow needs to go to where it's forming the bond. It's forming a bond with the delta positive carbon, so we're going to have the curly arrow going to the delta positive carbon. Now, strictly speaking, you are supposed to point the arrow kind of next to the carbon, because that's where the bond will actually be, but your exam board is quite happy for you to just point them at the atoms, like I've done there. Now, of course, this can't be the only arrow that we're going to put on there, because that would result in carbon having 5 bonds. It's already got 4 bonds, that would be gaining an extra one. It is not stable with 5 bonds, and therefore a bond is going to have to break. The question then is, which of the bonds is the easiest to break? Well, there's 2 factors here which matter. The polarity of the bond. If something's extremely polar, it's more likely the electrons don't have to move as far to move onto another atom, and also the strength of the bond. Now, double bonds are very strong, but if we consider the 2 separate bonds within the double bond, the pi bond, which is the second bond, is quite weak. So actually what we're looking at here is we've got 4 bonds. We've got the sigma bond between the 2 carbons. We've got the sigma bond between the carbon and the hydrogen. Both of those are non-polar and relatively strong. And we've got the sigma bond between the carbon and the oxygen, polar but strong. And then the pi bond between the carbon and the oxygen, which is polar but weak. So it's the pi bond in the double bond that's going to break. And those electrons, of course, are going to move towards the thing that is more electronegative, which is the oxygen. So it's going to do that. That will, of course, make a negative oxide ion, or there'll be an O- on our molecule there, and then that will get involved in the next step. But we're not worried about that because we're only interested in the first mechanism. Okay, so that's the first part of the question. The second part of the question is to explain why NABH4 reduces the 2-methyl-butanol but has no reaction with 2-methyl-butene. Now, I've actually already discussed why the hydride ion is good at attacking the aldehyde, so we can already just write that down because I've already mentioned it. The second part of the explanation then is to explain why the hydride ion would not be attracted, or not, in fact, not want to go near the the C double bond C. So let's consider what would be happening in this scenario. Okay, so I've got a hydride and I've got my C double bond C. First thing, of course, to note is that that double bond is very electron rich, and there's no delta positive area on it. Now, because it's so electron rich and there's no delta positive, not only is the hydride not attracted to it, but actually it's repelled by it, and therefore it's not going to want to go near it. And there are all your marks. Now, it's worth pointing out that the logic that we've just applied there is applicable to any scenario. So you need to be looking at things from the perspective of what does this species want to do? Does it want to go near a positive ion, delta positive, delta negative? Does it want to go near a double bond? What things are going to be attracted to other things, and therefore what are they going to react with? And the same logic that we applied earlier, which is which of these bonds is likely to break. Those kinds of logic we can apply to any mechanism to help us figure anything out. Okay, moving on to question B. This is a pretty standard testing question. So a student attempted to reduce a sample but had insufficient NABH4. The student confirmed the reaction was incomplete by using a chemical test. So we have to understand what it is that we are turning our 2-methyl-butanol into, and of course what we're not successfully turning into, because that's kind of the whole point. So when we are reducing an aldehyde, we will be reducing it to a primary alcohol. Consider my sort of little chain here. On the far left, we've got the alcohol, or primary alcohol. The arrows I've got represent oxidation rather than reduction, because that's kind of normally the way we look at things. So primary alcohol to aldehyde to carboxylic acid. We, of course, are going from the aldehyde back to the alcohol in this reaction, but we're going to have a little bit of aldehyde left over. So we want to work out how we can tell apart the aldehyde from the primary alcohol. Now, you can't just use an oxidizing agent like potassium dichromate, because both the primary alcohol and an aldehyde will react with it. So we need to use one of the two specific examples that will allow us to identify an aldehyde rather than absolutely anything else. There's only two substances that can do it. The first one is Tollens reagent, and the second is Fehling's. And the colour change for those, I always use Tollens, that's my example. So that is the silver mirror, or for the Fehling's, you get a kind of red precipitate. So Tollens is your go-to chemical test just to prove that you got an aldehyde and nothing else. Okay, a lot of people make the mistake thinking that an aldehyde is not the only thing that can be tested for with Tollens, because Tollens in the process, actually the process that occurs is actually a redox reaction. So you could kind of maybe be tricked into thinking that a primary alcohol would also react, but it doesn't. The only thing that reacts there is the aldehyde. Okay, so question 2 is to, or 2A is to name and outline the mechanism for the reaction in step 1. Now, I always start these questions by drawing out the mechanism and then naming it afterwards, because if you can draw the mechanism, you can see what it is, and then you can name it from that. So, looking at what we have in step 1, we've got an aldehyde. So again, we're looking at aldehydes here. And we're going to a hydroxynitrile. Now note that we have a change in the number of carbons. Okay, so in the aldehyde, we've got propanol, which is of course 3 carbons, but then in the hydroxynitrile, we've gained a carbon, we've got 4 carbons. Whenever you are adding an extra carbon to something, and you've got a nitrile like this, then you're looking at the reaction between cyanide and and your aldehyde. Now, of course, it does tell you. It tells you you've got hydrogen cyanide, but it's kind of useful to kind of point out these little things that you can look for in your mechanisms, in your reactions. Okay, so we're going to start off with our aldehyde and our cyanide, and we're going to see what happens. Okay, so we've already looked at the way that aldehydes behave, and of course we know already that aldehydes react because they've got the delta positive and delta negative on there. Okay, we've got that polar bond. This makes the carbon relatively vulnerable, and it can be attacked by a nucleophile. We have a nucleophile, of course. We've got our CN minus, and we've got a lone pair which is on the carbon. You do have to just remember which atom it is that does the attacking from the cyanide. So it's the CN minus, it's the C. Now, of course, if that's attacking that carbon and forming a bond there, that is going to have to result in the breaking of the bonds. And like we've already said, we've got a pretty weak and polar pi bond between the carbon and the oxygen, and therefore that is the one that's going to break. And we end up with this as our intermediate. Now, it is worth noting at this point what has happened to the charge. We started off with a neutral substance and a minus charge, and we've ended up where they've combined together. But notice how the charge started off, the overall charge started off as -1, and it's ended as -1 as well. So note, we always have a consistency in the charge as you go through your mechanisms. We do, of course, have the charge moving locations, but actually this all makes sense according to the arrows, doesn't it? Because we start off with a carbon, so our carbon, which is on the nitrile, starts off with that lone pair on it, and now it is sharing that lone pair, that pair of electrons, with the carbon. So it has lost some of that charge. The carbon, though, doesn't become negative because the carbon has lost one of the bonds that were in the double bond over there. And that electron has moved onto the oxygen. So you can see how the charge has moved from the nitrogen to the carbon, to the carbon, to the oxygen. Now, of course, that's still an intermediate that we've made because we have conveniently got some H+ ions present. So, again, applying our logic to figure out what's going on, we've got a negative ion and we've got a positive ion. They're going to pretty happily want to form a bond between them. And again, make sure you draw your lone pair on, and then the oxygen is able to attack the hydrogen. Now, the step earlier on in the reaction was a nucleophilic addition step. And therefore we've answered the question, named the mechanism. The second step is actually an acid-base, is a neutralization step, where you can see that the oxygen there is actually acting as a Lewis base. I mean, it's also acting as a regular base as well. It is accepting a hydrogen ion, but actually you can see how it's donating those electrons to the hydrogen ion. So it's acting as a Lewis base. So, mechanism, as we said, nucleophilic addition, because we're attacking that delta negative carbon. Sorry, the carbon on the nitrile is attacking the delta positive carbon, and of course we're going from having two separate substances to one substance, so it's an addition reaction. Okay, so moving on to question B part 2. B part 2 says to name the compound Q formed in step 2. So, the first thing to note is where the parent chain is, which is that. So that's our parent chain. The second thing, of course, to notice is our functional group, our main functional group, which is that. And then we have a sort of secondary functional group, which is that. I chose the priority based on the sort of standard priority rulings. You do need to know them. Most people who know them have more of a vague understanding because they use them all the time than actually kind of knowing the specific numbers of which one is more important. It's really straightforward in the case of carboxylic acids because they are always have the priority. And the clue that they always have the priority is that you probably don't know a prefix for them, whereas you do know the prefix for an alcohol group. So I'm just going to write the name up there, so we've still got it on the screen. Do note we do have to say the number that the alcohol group is on, because of course that carbon that it's on is carbon 2, this carbon is carbon 3, and this carbon would be carbon 4. So you could have 3-hydroxybutanoic acid, or you could have 4-hydroxybutanoic acid. You couldn't have 1, because then it would be part of the functional group, part of the carboxylic acid. Okay, so question B2 says that there are 2 stereoisomers that are formed by the dehydration of Q. Give the structures of these 2 isomers and name the type of stereoisomerism shown. Well, the 2 different types of stereoisomerism are geometric isomers and optical isomers. Now, optical isomers only form when you have 4 unique groups around a central carbon, whereas geometric isomers are what you get when you have an alkene. So we have to figure out what's happening in the reaction and see basically have we got an alkene or not. If it's an alkene, it's going to be geometric. If we haven't, then we're probably looking at optical isomers. Okay, so in the question, it says that we are dehydrating Q. So we've got 2 functional groups. We are not interested in the carboxylic acid. This cannot be dehydrated, so we're not interested in that. The alcohol group, however, can be dehydrated. So when you dehydrate an alcohol, you remove water and you make an alkene. Now, the interesting thing about this is that normally when you're looking at the dehydration of an alcohol, you can have the left-hand carbon to the one with the OH or the right-hand carbon forming the double bond. And you can have different isomers because of that. So you can actually end up with structural isomerism as well. In this case, you can't, because carbon 1, so the one with the carboxylic acid group on it, can't actually form a double bond because the functional group of the carboxylic acid uses up 3 bonds, which means it doesn't have the available space to have a double bond there. Okay, so you're actually going to form a double bond between carbon 2, which is where the OH is, and carbon 3, which is the one on the left. So what we're going to form is this. So the removal of water produces our alkene. I have intentionally drawn it in such a way where you can't tell what the 2 isomers are. But the question, of course, is asked for the 2 different isomers. Now, when it comes to stereoisomerism or geometric isomerism around a double bond, we are talking about the fact that the double bond is unable to rotate. And therefore, we are looking at what's coming off the different bonds. Okay, so we're going to have 2 different isomers. Okay, they both need to still be that molecule at the top, but they of course are going to be different ways round. So the first one I'm going to draw sort of both of them simultaneously. Okay, so we've got the right-hand side of our molecule to the right of the double bond, and now we need to do the left-hand side of the molecule. So that's one, but then we need to have it drawn the other way around, so we end up with that. And there are our 2 isomers. So, as we've already said, type of isomerism, geometric. Okay, so question 3 starts off with a pretty standard mechanism question. So we've got a reaction with HCN, and then we have to name the product formed. Okay, so there we have it. So things we're looking for is that the lone pair on the carbon on our cyanide attacks our delta positive carbon. Not bother drawing in the delta positive, but it is there. Of course, we've got the bond between the carbon and the oxygen breaking, which then results in our O minus over in our intermediate. Our intermediate can attack our hydrogen ion, and then we end up with our final product on the right there. In terms of naming it, so we've got our parent chain, which is that, and then we've got two different branches. So we've got 1, 2, 3, 4, 5. So it's pentane nitrile. Now the mark scheme does kind of say that you can write pentan nitrile. Other mark schemes I have seen do not accept that, so please do not write that. And then of course we've got a hydroxy group and a methyl group. The higher priority is the hydroxy. So alkyl branches are very, very low priority. The only thing they're higher priority than are halogens. So 2 hydroxy, 2 methyl. So 2 hydroxy, 2 methyl, pentane nitrile. Note the dashes between the numbers and the letters, but no dash between the methyl and the pentane. Okay, so question B is looking into whether or not you can determine the products from the reactions of Q and R by looking at whether or not they affect plane polarized light. Now, when it comes to deciding whether or not whether something's going to affect plane polarized light, there's 3 different options. Option number 1 is that something is optically active. Option 2 is that something is not optically active because it does not have a chiral center. And option number 3 is that it has no effect on the plane polarized light because it's a racemic mixture. Okay, so a racemic mixture is when you have 50-50 of the 2 different optical isomers, and one of them rotates the light clockwise and the other one rotates the light anti-clockwise, and they just cancel each other out. Okay, so when the question says, well, why can you not tell them apart? It's saying, okay, so neither of these are going to be optically active. So the question is, why? Okay, so here are the 2 products from the reactions of HCN with Q and R. So on the left, we've got the product from Q, and on the right, we've got the product from R. What we need to do is we need to look at to see whether either of them have a chiral center. So remember, a chiral center is when they have 4 unique groups coming off a single atom. In the case of organic chemistry, it's going to be a carbon. So the product from Q does. Carbon number 2 here has 4 different groups. CN is unique, CH3 is unique, OH is unique, and CH2, CH2, CH3 is unique. So that is containing a chiral center. But if we look at the product from R, we've got CN, which is unique. We've got OH, which is unique. But then we've got 2 identical groups coming out left and right. We've got 2 lots of CH2, CH3. So those 2 are not unique. So the product from R is not chiral. Now, we know that molecules that are not chiral are optically active. Okay, so that's not optically active. And if we can't tell them apart, then we must know that the product of Q is also not affecting the light. Okay, I'm trying to avoid saying not optically active, because although that's true, you need to have a little bit of explanation around it to explain why that's the case. So, the one on the left then, our product from Q, it is chiral, but it's not affecting the light, which must tell us that it's a racemic mixture. Okay, so going to our kind of our answer, our 3 mark answer, product from Q is a racemic mixture and therefore does not affect the light. And product from R does not have a chiral center and therefore is not optically active. Okay, so question 4. P, Q, and R have the molecular formula C6H12. All 3 are branch chain molecules and none is cyclic. P can represent a pair of optical isomers, Q can represent a pair of geometrical isomers, and R can represent another pair of geometrical isomers different from Q. So this question is not super obvious, but what it's saying is that there's 3 different structural isomers. And within each of those 3 structural isomers, there's different stereoisomers. So P has a structure where there are 2 different optical isomers, and therefore there must be 4 unique chains, 4 unique groups coming off a single carbon. So I'm going to start with my carbon in the middle. And of course, I know that it's got to be branched, although I know anyway because it tells us in the question. But actually, you know that it can't have 2 hydrogens coming off of it because that would be 2 groups that were the same and therefore not 4 unique groups. I am going to make a little bit of an assumption at this point, and I am going to assume that the carbon, one of the groups coming off of it, probably is a hydrogen. Now, this is a guess, but it's extremely likely, so it's a good place to start. So I've got 5 other carbons that I need to deal with, and I have a formula of C6H12. It's not cyclic, which means that it must be an alkene. Now, again, I'm going to make another, not necessarily true, but useful guess. I'm going to guess that one of the other groups is CH3. Now, this might not be true, and I might find that I have to change it later, but it's a useful starting point. So I've used up 2 of the carbons, and I've got to use up 4 more carbons. So I have to have the other carbons coming off like this. Now, this is starting to look like I've got 2 groups that are the same as each other, and therefore this isn't going to have 4 unique groups, but of course this is an alkene. So one of these 2 groups can have the alkene group in it, the C-double-bond-C, and the other one doesn't. So now, once I fill in all my hydrogens, I have 4 unique groups coming off. And there we have it. Structure for P. Okay, so structure for Q. So it tells us that we have a pair of geometric isomers. So we want to start by framing it around our double bond. Now we know that we have to have different things coming off the 2 carbons. So, sorry, different things coming off of each carbon. So we can't have like this, for example. That wouldn't have a pair of geometric isomers. So we can't do that. It's not necessarily the case that there's a hydrogen on in any of them, but actually I'm going to kind of go out on a limb and say, yeah, it's probably going to have a hydrogen on one of them. Now, we said it can't be on carbon 1. I'm going to place it on carbon 2. Okay, so here is this is where we're kind of building from here. Now, we've used up 3 of the carbons, which means there's 3 carbons left. It would be really tempting to have C3H6 7 here and a hydrogen here. Now that does have geometric isomers, but it's not branched. Has to be branched. So what I'm going to do is I'm going to suggest that we have a CH3 here instead, and then C2H5. So you can see the kind of process where I've made some assumptions in doing this, but it still kind of works out if you just kind of run with it. Okay, now the last one is the trickiest one because you've kind of exhausted the simple options. We know that it still is based around a CC double bond, and we know that it can't be on the N carbon. So actually we can start off with this bit here, absolutely fine. Now, we can't just change things around. We can't just swap the CH3 and the C2H5 because that would just be the same molecule. It would be the other isomer of it. The trick here is realizing that you can have the branch somewhere else. So if you were to put the hydrogen here, you can see that we can have the branch here instead. So we can have a CH3, CH3, H. So still branched. We got our branch on the right here. Still has geometric isomers. Fits all the requirements. Okay, so the first part of question B is just a definition. You just have to know this. So a racemic mixture is equal mixtures of optical isomers or equal mixture of enantiomers. It is really important that you say the word equal, because if you had, 75% of the R form and 25% of the D form, then you would still have an optically active mixture. Now the explanation. So I've drawn out the first step of the mechanism there, and it's not immediately apparent why you would end up with a racemic mixture if you were to look at it from this perspective. However, if you redraw this, but looking at the geometry, it's a little bit clearer. So I'm just going to draw it down below in the question part 2, and you'll hopefully be able to see what I'm talking about. Okay, so here's my butanone, and I've drawn it out with its geometry. It is, of course, it has 3 bonds coming off that carbon. There's no lone pairs, and the fact that one of them is a double bond makes no impact. So what we have is a trigonal planar molecule. And that trigonal planar molecule can be attacked from 2 places. It can be attacked from underneath, or it can be attacked from above. When it attacks from above, you end up sort of pushing those bonds down and you get one shape. And if you attack it from below, you push the bonds up and you get a different shape. So this is what you get if you attack it from above, whereas what you get when you attack from below looks like this. Now, of course, I've drawn it from a very different perspective to try and show you where the CN is coming in. But if you look at which bonds are next to each other, then you'll see that they're not the same as each other. So if we look at the top one, we've got the OH and the CH3 next to each other, and the CH3 being next to the C2H5, whereas if you look on the one below, the C2H5 is next to the OH, not the CH3. So it's a different enantiomer. So bringing us back to the question, then the explanation is simply that we have a planar molecule around the central carbon, and it can be attacked from either side, And not only can it be attacked from either side, but it's equally likely to be attacked from either side. Okay, let's move on to question part 2, which is to identify the reagent and draw the structural formula for T and U. So I gave you a hint earlier on in this video about looking at the number of carbons. So not only have we added a nitrogen, obviously we've gone from butanone to our U, which has a nitrogen on it, but also we've gained a carbon. We've gone from 4 carbons in butanone to 5 carbons in our final product. We are therefore looking at the attacking of a cyanide ion, and we're making a nitrile. Okay, so I've already kind of given that away with my explanations for the previous question, but that's what we're doing. Now, in terms of a reagent, you need something that's going to provide Cn-. Now, the mark scheme says that you can use HCN. It is fine, it does work, but actually KCN followed by an acid is a much more reactive mixture. So that's what I would be suggesting. So KCN and a strong acid, so HCl or H2SO4. It is worth noting, and it's important to realise that the word reagent means the full chemical compound, so potassium cyanide, not just cyanide, not just Cn-, is the full thing, so potassium cyanide, so KCN. Then we have to work out what T and U are. So we've pretty much already shown what's happening in the mechanism, where we're going to form that hydroxynitrile, like this. And then when we are trying to work out what's going to happen in U, we have to kind of basically pay attention to the fact that we've lost the OH. It has also told us that it's a dehydration reaction, so we're dehydrating an alcohol, which means we're going from an alcohol to an alkene. Now, of course, there are 2 possible ways to form this alkene, because we've got 2 adjacent carbons to the carbon with the OH on it, and either one of those can get involved in the dehydration reaction. So we've got 2 potential possible structural formulae, which will look like this. However, it tells us in the question a little bit more information. It tells us that U can represent a pair of geometrical isomers. So we have to work out which one of these 2 options is the one that can form geometrical isomers. And if I draw out my bonds, you will see that the bottom one cannot. So we've got 2 groups here which are not unique to each other. So these 2 are exactly the same. So there's no case of geometric isomerism here. So it's not the bottom one. Get rid of that. It must be the one that I've got left there. Okay, so moving on to question 5. We've got a multiple choice question. Which one of the following reaction mixtures would give a product capable of exhibiting optical isomerism? So we're looking for something that's going to create a chiral center. In terms of what we're going to make in each of these cases, for A, we're going to make this, neither of which contain chiral centers. B is going to make this, which does not have a chiral center. C is going to form this, which does not have a chiral center. So it must be D. Let's see what D makes, which of course has a chiral center. At this point in the test, you could probably just select D based on the fact that it's on the right, it's clearly about the right substances, but it's worth working it out because you won't have that clue in your actual exam. Okay, so moving on to question 6. So in each of these cases, we are going to be reducing them. The first one, of course, is an aldehyde, which goes from having that to that, which is not chiral, so it can't be that. Question B will form this, which does in fact have a chiral center. We've got 4 different unique carbons, different unique groups on carbon 2. And of course will be a racemic mixture, because the hydride ion can attack from above and below the plane, and it will do so equally likely. Just quickly looking at why the answer isn't C and D. So C, you've got there are 2 carbons on the left and 2 carbons on the right of the carbonyl carbon, which means that when you reduce it, you end up with C2H5 and C2H5, and therefore you don't have a chiral center. And then looking at D, it's just another aldehyde, just happens to have a C1C in it, so it's just the same as answer A. So the answer, of course, is B. Moving on to question 7. So which of the following reactions involves nucleophilic addition? So A is, of course, an addition reaction, but it's got HBr attacking the C++C. C++C is electron rich, which means that HBr is acting as an electrophile, so it is not A. Question 2 is the reaction between an alkene and chlorine, so that is a substitution reaction, and it is free radical, so that's free radical substitution, so it's definitely not that. Question C is the OH minus ion is attacking the delta positive carbon, so it is a nucleophilic reaction, but of course this is a substitution reaction, not addition, which leaves D, which of course is an addition reaction. You can see we're going from 2 reactants to 1 product, and the Cn minus, of course, is attacking the delta positive carbon. It is acting as a nucleophile. So the answer is D. Question 8. In which of the following mixtures does a redox reaction occur? So we've got ethanal and Tollens reagent. So Tollens reagent is, of course, a silver ion in the presence of 2 ammonia ligands. That silver ion is turned into silver, so it is being reduced to form silver, which we then see as the silver mirror. If you're reducing the silver ions, then the ethanal must be being oxidized, and therefore it is a redox reaction. It's worth noting, of course, that this must be a redox reaction because you can tell apart ethanal and or an aldehyde and a ketone, and of course the difference between them is that the aldehyde can be oxidized, so it must involve oxidation. The other options, though, so let's just check the other options, see what's going on with those. Ethanoyl chloride and ethanol. So ethanoyl chloride, if you've not come across it, which you may not have done at this point in the course, is very similar. It is a derivative of a carboxylic acid, and therefore they react in a condensation reaction. Ethanal and hydrogen cyanide is a nucleophilic addition reaction, and D is a neutralization reaction. So, yeah, A is the answer. Question 9. How many structural isomers with the molecular formula C5H10O react with Tollens reagent? Okay, so step 1 is knowing what Tollens reagent will react with. It will react with an aldehyde. It won't react with a ketone, it won't react with alcohol, won't react with carboxylic acids. So we're looking for all the different structural isomers for C5H10O, that is an aldehyde. Starting from the first one, of course, is just going to be the straight chain, like so. The second one then is going to have a branch. The third one is placing a branch somewhere else. And the fourth one is having 2 branches. And those are our options. So the answer must be B. Okay, so that brings us to the end of this video going through the Carbonyls and optical isomerism test. If you have any questions about any of those questions, or you would like anything to be explained further, then please do leave a comment. And if you enjoyed the video, do act like a nucleophile and attack that like button. I'm sorry, that was terrible.